Hi everyone, in this video I am solving two questions in joint CSIR UGC net held in February 2022 in the area of Rhiannon which is in part B. The first question is let S is equal to set 1 to etc 100 and let A equal to set of 1 2 3 etc 10 and B equal to set of 41 42 etc 50. What is the total number of subsets of S which have non-empty intersection with both A and B? Options: option A 2 raised to 100 by 2 raised to 20, option B 100 factorial by 10 factorial into 10 factorial, option C 2 raised to 80 into 2 raised to 10 minus 1 whole square, option D 2 raised to 100 minus 2 into 2 raised to 10. Here A is equal to set of 4 1 2 3 etc 10, so A contains 10 elements, and B is equal to 41 42 etc 50. B also contains 10 elements, and note that A and B are independent. Now we just consider W subset of A union B such that W intersection A is equal to mod W intersection A is equal to 1, and mod W intersection B is equal to J. That is W contains exactly one element from A and exactly J elements from B. And since the cardinality of A is equal to 10, we can choose one element set from A in 10C1 ways and J element sets from J element subsets of B in 10CJ ways. So the number of possibilities for W subset of A union B such that W intersection A contains one element and W intersection B contains exactly J elements is 10C1 into 10CJ. Similarly, the number of possibilities for W subset of A union B such that W intersection mod W intersection A equal to I and mod W intersection B is equal to J is 10CI into 10CJ for 1 less than or equal to I comma J less than or equal to 10. Thus the total number of possibilities for W subset of A union B which intersects both A and B is sigma I equal to 1 to 10 10CI, sigma J equal to 1 to 10 10CJ. Note that we only consider those W which is subsets of A union B, not whole set S which intersects both A and B. Now, sigma I equal to 1 to 10 10CI, sigma J equal to 1 to 10 10CJ is equal to sigma I equal to 1 to 10 10CI into by the binomial expansion we have sigma J equal to 1 to 10 10CJ is equal to 1 plus 1 raised to 10 minus 1 which is equal to 2 raised to 10 minus 1. So sigma I equal to 1 to 10 10CI into 2 raised to 10 minus 1. Since I is independent of 2 raised to 10 minus 1 is independent of I, so we can take it outside. 2 raised to 10 minus 1 that is equal to 2 raised to 10 minus 1 into sigma I equal to 1 to 10 10CI, which is equal to 2 raised to 10 minus 1 into 2 raised to 10 minus 1 which is equal to 2 raised to 10 minus 1 whole square. So the total number of possibilities for W subset of A union B which intersects both A and B is 2 raised to 10 minus 1 whole square. Or if we want to find, we can find the number of elements or subsets of A union B which intersects with both A and B in another way also, without using the combination. Suppose W subset of A union B intersects with both A and B, then W can be written as W is equal to W1 union W2 such that W1 subset of A and W2 subset of B such with W1 W2 not equal to 5. Since we have assumed that W intersects with both A and B, so W1 W2 not equal to 5, and also W subset of A union B, so W1 we can write this as W is equal to some W1 union W2 such that W1 subset of A and W2 subset of B. Since W1 is a subset of A which is not equal to 5, we have 2 raised to 10 minus 1. That's the power set of the cardinality of power set of A excluding 5 possibilities for W1. And similarly there are 2 raised to 10 minus 1 possibilities for W2 So every subset, every W subset of A union B can be written as W is equal to W1 union W2. So the W1 subset of A and W2 subset of B, so, and vice versa. For any W1 subset of A, W2 subset of B, so with the W1 comma W2 not equal to Y, we have W is equal to W1 union W2 intersects with the A union B. So the total number of subsets of W subset of A union B intersects with both A and B is 2 raised to 10 minus 1 into 2 raised to 10 minus 1 possibilities. We only consider the total number of subsets of A union B which intersects both A and B. We have to calculate the total number of subsets of the whole set S which intersects both A and B. So let W be a subset of A union B which intersects, just fix a W subset of A union B which intersects both A and B. Then for any W dash subset of S minus A union B, we have W union W dash intersects with A and B, since W intersects with the A and B, both A and B. So for particular W subset of A union B which intersects A and B, we have that for any subset W dash of subset of S minus A union B, we have W union W dash intersects with A and B. Since A contains 10 elements and B contains 10 elements and A and B are independent, we have S minus A union B contains 80 elements. So the possibility number of possibilities for W dash is 2 raised to 80 elements, that is equal to the power number of elements number of subsets of S minus A union B. So for a particular W subset of A union B which intersects A and B, we have 2 raised to 80 possibility. So we have the total number of possibilities is 2 raised to 80 into 2 raised to 10 minus 1 whole square possibilities. Since we have that 2 raised to 80 into 2 raised to 10 minus 1 whole square possibilities, if Y is a subset of S which intersects both A and B, then Y can be written as W union W dash, such that W is a subset of A union B and W dash subset of S minus A union B. Then it counted in this 2 raised to 80 into 2 raised to 10 minus 1 whole square possibilities. So the answer is 2 raised to 80 into 2 raised to 10 minus 1 whole square. This is the one way for solving this problem. We can also use an alternative way to solve this problem. So I will also describe that. We have that to find the subsets of the S which intersects both A and B. It is enough to find those subsets of S which have an empty intersection with A or B. Then just minus it from 2 raised to 100, we will get the result. So for any subset which subset of S which have an empty intersection with A or B will be a subset of S minus A or S minus B. And also every subset of S minus B does not intersect with B, and every subset of S minus B A does not intersect with A. So the subsets which have an empty intersection with the A or B is equal to power set of S minus A union power set of S minus B. Since S minus A union B contains in both S minus B and S minus A, we have that S minus every subset of S minus A union B is counted in 2 times. So the number of subsets of W such that W intersection A is equal to pi or W intersection B is equal to pi is the number of cardinality of power set of S minus B plus cardinality of power set of S minus A minus cardinality of power set of S minus A union B. Since S minus A contains S minus B contains 90 elements and S minus A contains 90 elements and S minus A union B contains 80 elements, we have that cardinality of A of power set of S minus B plus cardinality of power set of S minus A minus cardinality of power set of S minus A union B is equal to 2 raised to 90 plus 2 raised to 90 minus 2 raised to 80, that's equal to 2 raised to 91 minus 2 raised to 80. And then the total number of subsets of S is equal to 2 raised to 100. then just minus it from our precedent. Is equal to 2 raised to 100 minus 2 raised to 91 minus 2 raised to 80, that is equal to 2 raised to 100 minus 2 raised to 91 plus 2 raised to 80, that is equal to 2 raised to 80 into 2 raised to 20 minus 2 raised to 11 plus 1, that is equal to 2 raised to 80 into 2 raised to 10 minus 1. Now coming to the second question, we have to find the limit n tends to infinity 1 by n whole 1 plus root 2 plus cubic root of 3 plus etc. nth root of root n, which is equal to 0. Option A. Option B, this is equal to 1. Option C is equal to 2. D does not exist. We have that Cauchy first theorem on limits. Thus, if limit n tends to infinity an is equal to n, then limit n tends to infinity 1 by n, a1 plus a2 plus etc. an is equal to l. So here this we can, if we take an equal to nth root of 1 by n, this is the form of 1 by n plus a1 plus a2 plus etc. an. So we can apply Cauchy's theorem. So if we want to find 1 by n into 1 plus 2 raised to 1 by 2 plus 3 raised to 1 by 3 plus etc. n raised to 1 by n, it is enough to find limit n tends to infinity n raised to 1 by n. So let limit n raised to 1 by n is equal to a log, and then put logarithm on both sides. Since n tends to infinity, we get infinity raised to infinity, we can't use that. So just taking log in both sides, log L is equal to log limit n tends to infinity n raised to 1 by n. Then since log is continuous, we have log limit n tends to infinity n raised to 1 by n, we equal to limit n tends to infinity log n raised to 1 by n, that's equal to limit n tends to infinity 1 by n log n, that's equal to limit n tends to infinity 1 by n by 1 by Hospital rules. Since log n tends to infinity, log n tends to infinity and n tends to infinity, we get the limit n tends to infinity 1 by n log n. This is in an infinity by infinity form, so we can use Hospital rule. So a limit n tends to infinity 1 by n log n is equal to limit n tends to infinity, the derivative of log n, but that is 1 by n, by the derivative of n, that's 1, so which is equal to 0. That implies log L equal to 0, which implies L is equal to 1. Thus limit n tends to infinity 1 by n into 1 plus root 2 raised to 1 by 2 plus cubic root of 3 plus etc. nth root of n is equal to 1. We can also find limit n raised to 1 by n by using Cauchy's second theorem on limits, which states that if a and b a sequence of positive real numbers, then limit n tends to infinity a n raised to 1 by n equal to limit n tends to infinity a n plus 1 by a n. Since limit n we want to find limit n tends to infinity n raised to 1 by n, if we take a n is equal to n, we can use the Cauchy's second theorem on limits. So limit n tends to infinity n raised to 1 by n is equal to limit n tends to infinity a n plus 1 here, a n plus 1 n plus 1 by n, that's equal to limit n tends to infinity 1 by 1 by Hospital's rule, since we get infinity by infinity form, that's equal to 1.